One of the goals of the previous exercise was to illustrate to you that correlation coefficient and cosine similarity are going to differ from each other when the means between the two variables is very different and different from zero. And that leads us to exercise 2, which is all designed to really highlight this distinction and really hit home this point. Okay, so what we are going to do is create two vectors, two variables, both containing the integers, or both start from the integers 0 through 3, so it's a very small data set. And then the second variable equals the first variable, so 0 through 3, but then we add some offset. And that offset varies between minus 50 and plus 50. So basically, we have a large mean offset shifted to the left, no mean offset, and then large mean offset shifted to the right. And then we just plot both of these. Now, not surprisingly, the Pearson correlation not only doesn't change for these mean offsets, obviously, because the first step of computing a Pearson correlation is to demean the variables, but that correlation is exactly 1 all throughout everything. And then we get to cosine similarity, and that is strikingly different. So it starts off as being negative, even though both numbers are moving in the same direction. So they're moving in lockstep with each other, but we still get a negative cosine similarity. And then that shoots up to 1 when the mean of both vectors is 0. And then it comes down a little bit, but it stays quite robustly positive. Now, in the book, in this chapter, I discussed why this is the case, whether it's bad. The answer is it's not bad. It's just a very different interpretation. And yeah, it's just something to be aware of in machine learning applications, that Pearson correlation and cosine similarity are designed for different kinds of data. It's not safe, or it's not appropriate to use them interchangeably and expect that they are the same, even though they appear to be really, really computationally similar. Okay, so let's switch to Python, and I'll show you how I created this figure. So here I create the first vector. I call this A. You can see it's just numbers from 0 through 3. And then I define a vector of offsets, which goes from minus 50 to plus 50. And then the simulation is actually pretty straightforward. I just have a loop that goes over all of these elements in the offset, and I store the results, which is the correlation coefficient and the cosine similarity, using the function that I created in a previous exercise for variable A. And then this is variable B, which is literally variable A plus this offset. Okay, it's that simple. Once you have this function, it's, this exercise is pretty straightforward. Actually, most of it is just about plotting and getting the plot to look nice. So here you see the results. Again, if you are curious, you don't understand why these are so different from each other and what to make of that, it's something I discussed in more detail in the book chapter. Basically, these are both perfectly valid measures of similarity between vectors, but they start from very different assumptions, and therefore they can give very different results. They can also be identical under some conditions.